that curved mirrors do follow the law of reflection, right? All reflection follows the law of reflection. Now, if we do get to curved mirrors today, we're just going to kind of be doing part 2 of the lab that you guys handed in today. And then that should be a good introduction to set us up to be able to address all those objectives. Okay, so we want to finish up with plane mirrors. I think we did see one figure of a plane mirror last time where we were answering the question like how tall of a mirror do you need to see your whole body? And was it Magna that we were using for that? Remembering correctly? All right. And we said that if Magna is standing over here, then the image that she sees, well, first of all, she only needs a relatively small portion of the mirror. So about half of her, just about exactly half of her total height. And if she looks right here, she should see light coming from her toes. Oops. So it looks to her like her toes were back here, right? And then we've had a virtual, I don't know how she's turning from a stick figure into a regular figure, but it looks to her like she's back here, and that's why we call that a virtual image. Right? We said that she's looking in this direction to see her toes, so she's smart, so she knows that she's not really behind the mirror. But if we can kind of erase our smartness, we would think that there's somebody behind the mirror kind of looking at us. How do animals do with mirrors? Not so good? Magna, what have you seen?
Well, I have 3 birds at home.
Okay, 3 birds, yep.
So when they see a mirror, they kind of freak out and start hitting it really fast.
Okay. And birds are kind of smart or kind of dumb?
They're kind of dumb.
Yeah, they call it somebody like bird-brained, like that's an insult, right? Because they're not very smart. All right, so birds don't do well with mirrors. They're not smart enough to know that what they're looking at is really in front of the mirror. They think it's behind the mirror. So that's a great example of plane mirrors forming a virtual image, right? It appears that the image is behind the mirror. Now, more specifically than plane mirrors always just making things look like they're behind the mirror, there's some pretty easy rules to further describe that image. So the image that a plane mirror is allowing us to see is always located behind the mirror, but it's always located the same distance behind the mirror as the actual object is in front of the mirror. All right, so here we have 3 people looking at something. All right, who's this one? Who's this one? All right, fine. Doesn't matter. Doesn't matter. So this guy's looking at this thing, sees it back here. Right? She's looking at this thing, she sees it back here. He's looking at this thing, he sees it back here. They all see it in the same place, and that place should be just as far behind the mirror as the real object is in front of it. All right? So the image, and that's called the image distance. The distance between the image and the mirror, that's called the image distance. The distance between the object and the mirror, that's called the object distance. So if we have a plane mirror, the object distance, DO, is always equal to the image distance. Later on, we're going to say that the image distance is negative if it's behind the mirror. We don't really have to worry about that today, but that's just a little foreshadowing of next class. And the image size should be the same as the object size. So if the object is the same size as our head, right, then the image should still appear to be the same size as our head. That one gets a little tricky because if you move like further away from the mirror, the thing looks smaller, but the real object looks smaller also, right? So that can be a little bit tricky, but whatever. The object height should be the same as the image height. All right, so if a squirrel is sitting 2.5 meters in front of a mirror, then its image, when we look at it, should be located 2.5 meters behind the mirror. And I don't know that there's really much additional complexity to plane mirrors than what we've said already. We should give this another shot, right? We weren't able to watch this video last time, if I remember correctly. Let's give it another shot. I mean, we talked about it, and we said that some of you guys have been in a mirror maze. I still would like to know where. I've only been in. The only thing I've found is like corn mazes. They don't do much
There's a
for
fun house in the boardwalk there.
boardwalk.
I mean, it's terrible because
Jenkinson's where like in the
it's at
inside the fun house, or it's
it's the first part of it.
is that only open in the summer, or is that open all year?
Summer. It's nice in the summer though, man.
That's barely spring. I can't wait till summer. All right. All right. So again, we got mirrors everywhere, and this guy, he has no idea if he's looking at a mirror or if he's looking at like open space. That's why he keeps like touching with his hands. He has his hands out in front of him. And I think we did see last time that they do make you wear gloves in these things. Otherwise, you'd be fingerprinting up the mirrors, and then it would be way easier to tell. So this guy has no idea. He's probably not particularly dumb, right? But the builders of this mirror maze have set it up to take his 30 years of experience with mirrors kind of out of the equation, and he has a real hard time telling if he's looking at open space in front of him or reflected images of open space which appear to be behind the mirror. Right? So if we have super clean mirrors, it can be very difficult to know if we're looking at a mirror or not. At Jenkinson's, do they make you wear gloves?
No, that's why it's
Ah,
not. It's kind of dirty.
I'm not going to go there.
It's kind of dirty now.
I mean, I don't think they can do that anyway because, I mean, unfortunately, I think you end up getting like a lot of like inebriated people like on the boardwalk, and I think that
That's hard to
breaking the
I was a little.
Ben,
Is there a strategy to going through a mirror?
is there a strategy? I've never done it.
You've never been in a mirror
I don't
maze?
think so. I don't know what you could do. I mean, I guess if you had a few people. Well, I was just thinking about that. But then what is that going to tell you?
What if it
You'll
reflects off of
you'll
it,
see
then
the
don't go
dust.
into that because that's a mirror.
But there's mirrors everywhere.
Yeah,
It'll
I just
bound to
don't-
reflect off something.
I mean, that's the first thing that occurred to me is use a flashlight, but how's it going to look different if I have a mirror right in front of me versus if there's a mirror like 10 feet in front? Like, I don't know.
Ball of string.
If it's really all mirror, I don't
That's
know.
still just like.
Alright, one conversation. I'll let everybody talk. Richie.
If you were to go in front of each opening and shine the light, then the one that's open would reflect that.
But that's
There'd
just
be a
like
mirror
touching the
over
mirror.
But if everything's lined with mirrors, there's going to be a mirror like further in front. So I don't know. I'm just having a hard time conceptualizing like how the flashlight's going to help me. I mean, I think the strategy is Frankenstein wall, right? Like the guy was doing. Jeff.
I mean, also sometimes you can tell like it's not like a well put together maze. Like that one was better, but the one in Jenkinson, you can usually tell because like if you look at the edges of the walls, you can kind of see that it's like bent just a touch,
Yeah.
and like
Yeah,
sometimes
I don't
that
know.
Look at the like seam on the floor.
Look at the seam on the floor. I don't know if there's no seam.
Jenkinson's
Alright, anyway.
Take a feel.
Now, the question that was up here when you walked in, and I don't quite know what, if anything, we're going to get out of this, but I asked in which rooms of your house do you have mirrors? So obviously, you're going to have mirrors in the bathroom, right? Because that's where you like brush your teeth, put makeup on, like put your contact lenses in, whatever. Let's see, so what are other types of rooms? Kitchen, anybody raise your hand if you have mirrors in your kitchen? So like one of them, so kitchen, no. What other kinds of rooms do we have? We've got like dining room. I don't know that everybody has a separate dining room, but dining room. All right, and then fine. So that's a lot of you. We got bedroom. Ooh, so that was a yes. Bedroom. Wow. Was it? All right. I guess because you're getting dressed, you might want to see and straighten your tie, whatever fun. Living room kind of thing. Few of you. What other kinds of rooms do we have? Basement? Really? It's like 5. I was gonna say, like, it's not really. This was one person. These were a whole bunch. This was like in between. What else? Attic.
I lived in my attic.
What else? What I missed? That's about it? Alright. Sorry, the bedroom we figured out, that's because you're like getting dressed, so fine. We don't need to discuss that. Kitchen, right? Not there. Attic, no. Basement, no. Why do you have mirrors in your living room?
Because my mom likes mirrors.
Because your mom likes to look at herself?
Yeah, no, she likes mirrors. She gets
Your mom
them.
likes mirrors.
I
Okay.
don't know
Ruchi?
why.
Usually like makes the room look bigger.
Makes the room look bigger.
That's why,
We just
like,
had
when
another
we were, like, decorating our house, the lady that was like, what we put on.
All right. So Ruchi had an expert say put mirrors in. Put mirrors in because it makes the room look bigger. All right. Will.
In our living room, we have our paper rack.
Okay.
There's like a mirror like that like, attached to it.
Okay. Okay. And. So a mirror makes the room look bigger. Does that sound right? Is that kind of consistent with things that we've said? I think so. I think it's totally consistent, right? Because we've said that all of the images that form in a plane mirror appear to be behind the mirror. Even, if we know that it's not, we still have to be smart to know that the things we're looking at aren't truly located behind the mirror. So we really do have to make that conscious decision, right? If you see something like this on the wall, right, depending on what you're seeing in it, it might really look like a window, right? And we're getting light coming off of the surface, more light coming off of the surface than we would be if it was just light painted. So absolutely, it's a trick of interior design to put wall mirrors up to make a room appear larger than it really truly is. So yeah, so Ruchi's expert, they knew what they were talking about. So let me just cut to one image that I found. So what is HGTV? What's that?
Oh, that's
Home and garden TV.
Home and Garden TV.
Yeah.
I love that.
I don't even know if I have that channel.
It's,
You probably do. Yeah.
Apparently their server's not very good. So there's this 10 tips for decorating with mirrors. So I'm just going to cut to tip 3. Double the space. Add mirrors to any space you want to visually expand. The location and placement of the mirror are key when utilizing them. You want to ensure that it will not create undesirable reflections and will allow it to maximize its innate qualities, blah, 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 blah. So make it look bigger than it actually is. So yes, if you have a small living room that you want to look bigger, we will get tricked, at least subconsciously, into thinking the room is bigger if we put mirrors there. Absolutely. Absolutely. Right? Because they always make virtual images. It looks like there's stuff behind the mirror, even though there's not. All right, so let's do one quick question, and then I think we'll shift to, we'll see if there are any other questions about plane mirrors, and then shift to review. All right, so you think you have some kale stuck in between your teeth, right? Molars, back of your mouth. You look in your bathroom mirror, right? It's a plane mirror, and you see something that looks like it's 12 centimeters behind the mirror. Where is that thing actually located? We got 4 answers. We got A, 12 centimeters into your mouth, 12 centimeters in front of the mirror, 12 centimeters behind the mirror, or no, there's nothing there. The mirror's just playing a trick on you. All right, what do we like? Oh, I heard some A's, I heard some B's. Some A's, I heard some B's. If it appears to be 12 centimeters behind the mirror, that's making reference to the image distance, right? How far the image is behind the mirror. The object distance has to be the same as the image distance. So the piece of kale, or whatever it is that looks like the piece of kale, should be 12 centimeters in front of the mirror, right? I don't know how far into your mouth that looks like. It depends on how far your mouth is from the mirror. But the object should be 12 centimeters in front of the mirror for sure. All right, other issues, other questions about plane mirrors, flat mirrors? Yeah?
I don't know if this is like a plane mirror, but how do you get the mirror that like you look into one way and it gives a reflection, the other way you can look through it and see the person?
So I think in this section we haven't talked about what the mirror like physically is. Right? So what is this made of? It's got glass, okay, and the glass plays little role, actually no role, in the reflection of the light. What else is there?
Isn't there metal behind it?
There's something. There's some reflective coating on the back. So apparently on the reverse side of it, it's not reflective, but there's a thin layer of stuff painted onto the glass that is really good at reflecting. All right. So and then what's the purpose of the glass? Just to protect that layer. right, so it doesn't get all scratched up. All right, so a mirror is glass and a reflective surface. We could construct a mirror that had a reflective surface, but that allows some of the light to go through it. Right, so not fully opaque, but maybe transparent. Right, so if we allowed a small fraction of the light to get through, but most of the light to reflect, that would be kind of cool. Because if you're on this side of it, the illuminance or the luminous flux from the front of it would be pretty high, so you're going to see nice reflected images. But if you're behind it, right, if you can block out other sources of light, you should be able to see the little bits of light that are coming through. That's all that a two-way mirror is. It's just allowing a small percentage of the light to come through, most of it to reflect. And that's all that we need to explain that. Other issues with plane mirrors? All right, so let's shift into review, and then we will make sound with your mouth wind instruments, and I think we'll have enough time to work on our first exposure to curved mirrors as well. All right, so I think I said last class that we're going to start the test with the end of chapter 14, because I did have reflection and refraction on the last test, I think, but I definitely didn't have some of the other parts of chapter 14. All right, so chapter 14.3 was what the heck happens when a wave reaches the end of a medium. So here I have an image, and we have two different media here. We have one, so this is water, right? These are water waves. We have deep water over here, and then shallow water over here. And the wave energy will act differently in those different depths of water. So when the wave reaches the second medium, it's either going to reflect off of that boundary, which now we've talked about a whole bunch more, or it might refract into that second medium, right? So chapter 14.3 started with those two potential outcomes when energy reaches a boundary. And the energy that's reflecting, right, should have the same speed as the incident energy. It should have the same wavelength. It should have the same frequency. It'll have a different amplitude probably if some of the energy refracts, but all of the other wave properties should be identical for the reflected ray. For the energy that refracts into our new medium, the frequency has to stay the same. The only thing that controls the frequency is the source of the disturbance, the source of the wave. The speed should be different, right? The only thing that controls the speed of a wave is the medium that it's traveling through. So if we have a new medium, we probably have a different speed, right? And since speed is frequency times wavelength, if the speed changes and the frequency stays the same, then the wavelength does have to change. And that's why this diagram is showing a shorter wavelength for these refracted waves. Right? Apparently, the speed in the shallow water is less than the speed in the deep water, right? Because if the wavelength is decreasing, then that has to mean that the speed decreased. All right, so other follow-up questions from anybody about wave energy reflecting or refracting as it reaches a new medium or a boundary? Okay. And then the stuff that I know I didn't include on your last test was interference of waves, right? So we called that superposition of waves, because if we have multiple waves, they do get kind of superimposed on each other. So in this diagram, we have kind of three different examples of interference. We have this first example on the left, right? So we have this wave that we are superimposing on this other wave. So we have these two waves passing through each other, probably traveling in opposite directions. And we have destructive interference here, because where we have a crest from this wave, we happen to have a trough from this wave. And then where we have a negative displacement on this one, we have a positive displacement on the other one. And because they have the same wavelength and the same amplitude, and they're in phase with each other, they completely cancel each other out, and our medium does not get displaced when they're passing through each other. So that's a pretty good example of complete destructive interference. In the middle, we have complete constructive interference, where we have equal wavelength, equal amplitude waves that are in phase with each other. We have a crest from one, at that same spot, we have a crest from the other. We have a halfway to a crest here on the one, we have halfway to a crest on the other. So these waves will, these ones in the first image, kind of the displacement subtracted from each other, and this one they're adding to each other. So we have constructive interference, and we kind of get our super pulse when they're overlapping. All right, questions about the destructive interference here or the constructive interference here? All right, what's this other one? Looks like constructive interference, but it also looks a little bit more complicated because those energies that we're adding to each other appear to have either a different wavelength or they're just not in phase with each other, right? The crest from this one doesn't actually match up with the crest from the other one, right? This one shifted a little bit to the right. So we still have constructive interference, but it's just a little bit more complicated than we had in this one, right? But we do still have, well, we have constructive interference actually in some places, but now that I'm looking at it again, I think we have destructive interference in other places. Like here, we start having a negative displacement on this wave, but we still have a positive displacement on the other one. So in, let's see, so what total region is that? That would be in between here and here. I think we actually have destructive interference where the energies are subtracting from each other. So this third one, and I don't think we really looked at anything like that back a few weeks ago, but it's not perfect constructive or perfect destructive interference just because these two waves are not in phase. They don't have their crests in the same spot of the medium or their troughs in the same spot of the medium. And then we did go one step further with interference when we looked at standing waves in chapter 14. So the standing waves that we saw had a string tied to the faucet at one end and then on the drill at the other end. And we saw that where the string was tied to the faucet, we had a node, right? We could not have any displacement of the medium there. So by default, we had to have a node. But then we saw different numbers of standing waves in between the drill and the faucet. So we saw, I think we did see one standing wave that had one antinode in the middle and then almost a node at the drill. We saw one that had an additional node in the middle. We saw one that had 2 additional nodes in the middle. I think we saw one that had 3 additional nodes in the middle. And where we had nodes, we have perfect destructive interference, right? So these standing waves were due to incident waves, right, interfering with the reflected waves. We were reflecting energy off the faucet, and we had interference of the reflected waves with the incident waves. If we had perfect destructive interference everywhere, or all the time, we had nodes, right? So a node has destructive interference 100% of the time, right? Whatever displacement the incident wave has, the reflected wave has an opposite displacement. So if the incident wave has a positive, the reflected wave has a negative, and the same amount of displacement. The antinodes always have constructive interference, but sometimes we have positive constructive interference, like on the top of our medium. Sometimes we had negative constructive interference, where we had troughs that were adding to each other, and then we had everything in between, right? So one moment we have crests interfering, maybe a half a second later we have troughs interfering, a quarter of a second later we actually have 0 displacement from the incident wave and 0 displacement from the reflected wave. So sometimes this spot on the medium actually isn't displaced, but other times it is. So we always have the same wave feature from the incident waves interfering with that identical wave feature from the reflected waves. So the antinodes are in a constant state of flux. They're constantly changing. The nodes always have no displacement at them. All right, so we saw that with the string. We heard that with our, with our resonance tubes, with the tuning fork, right? We heard constructive interference with sound. Right, so that brings us to sound. So chapter 15 was all about longitudinal waves, right? So sound waves are variations in air pressure. We have a compression if we have higher pressure than normal. We have a rarefaction if we have lower pressure than normal. So in this diagram, we have a speaker, right? So the speaker has a diaphragm that pushes out, in, out, in, out, in. When it pushes out, we push the air molecules together, creating a compression, and then when it pulls back in, we are kind of pulling on the air molecules, creating a low pressure region, a rarefaction, right? So sound waves are absolutely longitudinal waves. The loudness of the sound wave is most related to the amplitude, and then the pitch of the sound wave is identical, is synonymous with the frequency of that energy. We didn't really do, well, there was actually a little bit more. We did take a look at the human ear. We looked at energy transformations that occurred in the ear. We looked at the role of most of these different ear parts. So the main ear parts that I remember would be the external ear, right? The ear canal, the tympanic membrane. We had 3 different bones, right? On the other side of the tympanic membrane, we had the malleus, the incus, and then the stapes. And the point of that bone system was to amplify the vibration of our tympanic membrane to get higher pressure, to get higher amplitude waves delivered into the cochlea, and then the cochlea allows those mechanical vibrations to get converted into electric signals, which get sent to the brain. Right? So we want to at least have a rough understanding of those particular parts of the ear. I think the last thing in the first half of chapter 15, which we actually spent a good day and a half on or so, was the Doppler effect. So the Doppler effect was a phenomena that involved either a moving sound source or a moving sound detector, or not just sound, a moving wave source or a moving wave detector, or both, right? And we had shifts in the frequency and wavelength of the energy that's detected by the detector. So in this diagram, we have a police car on this side, this street, moving towards this guy. Wait, hold on. Which one's moving towards, one's moving away. This one I actually think's moving away. Yeah, that's a brake light. That's not a headlight. This is confusing. They look almost the same. This one's definitely moving away.
That one's coming forward.
Yeah, no,
Yeah, the
no,
one
no,
on
This
like
one's
on the
moving.
top.
I can look at the wavelengths to actually help me out. So sorry I fumbled that. This one's moving away. This one's moving towards. And they're emitting sound. They're also emitting light. Now this guy's standing still. Right? So this would be a kind of simple Doppler effect problem where we only have one moving thing. Because this car's moving away, right? The waves behind it are reaching the detector less frequently. Right? So we do have longer wavelength. We also have lower frequency, and they'll hear a lower frequency. This car is moving towards the detector, so they're going to detect the compressions and rarefactions more frequently, so they hear a higher pitch, and they also, with the waves, would seem to have a shorter wavelength, right? Since they're encountering them more frequently. This gets a little bit more difficult when the detector is moving as well. And we did have our Doppler effect equation, and remember there's only one version of it on the equation sheet. I did post a clean solution for that homework problem, right? I posted that yesterday. So if you wanted to see a cleaner solution, that's up there for you. And the tough part of our equation was what sign we use for the 3 velocities, right? So there's 3 different velocities in there. The v with no subscript at all is the speed of the actual wave. So if we're talking about sound in 20 degrees Celsius air, then that's 343 meters per second. The v with the s as the subscript is the velocity of the source, right? So that might be, well, all of these might be positive, might be negative. And then the v with the d is for the detector. That might be positive, that might be negative as well. I pretty much always use my source as the direction of my source's velocity is positive. Right? I pretty much always do that. You don't have to, but I always do that. In this scenario here, the detector's not moving, right? So the speed is 0. And then we need to make a decision about which direction the waves are moving, right? So in both of these examples, the sound is moving towards the detector. For this police car, we said that it was moving away from the detector. So if I made that my positive direction, then the sound would have to be moving in the negative direction, right? But on the other hand, in this example, we said the car was moving towards the detector, which I would call my positive direction for that other example.